Hey everybody, I'm Jule Krüger and I'm a PhD student at the University of Duisburg-Essen in Germany. In this video I will present research that I've done together with my supervisor Daniel Bodemer on how different types of interaction with augmented reality learning material have an influence on different learning processes and outcomes. In augmented reality, or AR, virtual elements are added into the real world. For educational purposes, this means that elements of the outside world can be added into pedagogical environments, or pedagogical elements can be added into the outside world. Through the various possibilities of AR, learning applications with many different features are created. But the question still remains: when and how is AR useful to effectively support learning, and which features do especially play a role in that? AR has been defined by Azuma as a technological system with three characteristics. It combines real-world and virtual elements, the elements are interactive in real time, and the elements are registered in 3D. Based on this, we formulated three characteristics of AR from a human-centered perspective: contextuality, interactivity, and spatiality. I will give you a short overview over contextuality and spatiality before diving into interactivity, which we focused on in the current study. Contextuality describes that virtual elements in AR are perceived in the context of the real environment, so that, if desired, a thematic connection between the two can be established. In this picture, for example, virtual information is placed directly over the respective plants, providing information that is relevant exactly at this place and time. Spatiality describes that virtual elements in AR are perceived to exist in the same three-dimensional space as real elements, and thus themselves have spatial properties like size and depth. This video shows a screen recording of an app in which the human heart can be seen in 3D and from different perspectives, showing its spatial structure. Interactivity, which we focused on in our study, describes that learners can interact with elements in AR. Through the unique combination of virtual and real elements, also unique interactive possibilities arise in AR. Learners can interact with both real and virtual elements directly, but they can also interact with virtual elements through the manipulation of real elements. Through this unique combination, elaborate interaction with AR learning material is possible. In this video, for example, a learner interacts with virtual components of a power plant by moving physical AR markers around. The virtual objects move with the markers and react by connecting when they are close to each other. Research on multimedia-based learning often states that mental engagement with learning material leads to learning, while physical engagement may even hinder learning. This is often based on cognitive load theory, which says that extraneous cognitive load that hinders learning should be decreased, while germane cognitive load that supports learning should be increased. Embodied cognition theory and, for example, the ICAP framework, on the other hand, state that physical interaction is necessary for learning and that more overt physical engagement with learning material leads to increased learning. The views have in common that they say that physical interaction with learning material must induce germane cognitive processes and not just extraneous load to support learning processes. Because of the unique interactive possibilities of AR, it is important to systematically examine how different forms of interaction with AR learning material have an influence on learning. The goal of this study was to compare learning with material that necessitates different degrees of mental and physical interaction. Hypotheses that we formulated based on cognitive load theory were that both a higher mental interaction and a higher physical interaction would lead to a higher knowledge and germane cognitive load, but that this influence would be bigger for mental interaction. We also hypothesized that higher physical interaction would lead to higher extraneous cognitive load. In a 2x2 between subject design, mental and physical interaction were manipulated, with both either higher or lower. Mental interaction was manipulated through the instructions given to the participants, while physical interaction was manipulated through the AR markers provided. 128 participants, which were mainly students, were included in the analyses. More women than men took part, and their mean age was around 22 to 23 years. In this short clip, the usage of the application used in the study can be seen. With the application, participants could build combined cycle power plants. Each component of the power plant has its own paper marker that it is anchored to. By placing the markers next to each other in the correct order, different power plants can be built. When a working power plant is built, energy output and efficiency can be viewed. Through this possibility to manipulate the real-world markers to interact with the virtual objects, it appears as if the virtual objects are inside the real world, leading to a sense of virtual object presence. As part of the experimental study, the participants had to answer different hypotheses on the different power plants. For this, the size of some of the components and the size of the whole plant could be changed. Mental interaction was manipulated through the instructions. In the low mental interaction conditions, an additional instruction was provided concerning the power plant configurations that needed to be compared to test the respective hypotheses. This additional information was not provided in the high mental interaction conditions. Physical interaction was manipulated through the AR markers. In the low physical interaction conditions, these were already clustered together into working power plants, while in the high physical interaction conditions they were separate, as was shown in the video. This resulted in the 4 experimental conditions. When both types of interaction were low, the participants just had to look for the marker cluster that were shown on the screen. When mental interaction was low and physical interaction was high, the participants built and compared the marker clusters that were shown on the screen. When mental interaction was high and physical interaction was low, the participants decided which marker clusters to compare and searched for them. And when both types of interaction were high, they also had to build those clusters themselves. To test if knowledge was influenced by mental and physical interaction, a 2x2 ANOVA was executed. No significant main effects were found, showing that both types of interaction separately did not have a significant influence on knowledge. But a significant interaction effect was found, showing that knowledge was higher when either mental or physical interaction was high, but not when both were high or low. These results do not support our hypotheses that both mental and physical interaction have an influence on knowledge with a high influence of mental interaction. To test if germane cognitive load was influenced by mental and physical interaction, another 2x2 ANOVA was executed. No significant main effects or interaction effect were found, showing that both types of interaction did not have a significant influence on GCL. These results do not support our hypotheses that both mental and physical interaction have an influence on GCL with a higher influence of mental interaction. To test if extraneous cognitive load was influenced by physical interaction, an independent samples t-test was executed. Although a slightly higher mean ECL score was found for the high physical interaction group, no significant differences between the groups were found, showing that physical interaction did not have a significant influence on ECL. These results do not support our hypothesis that physical interaction has an influence on ECL. Although the hypotheses we had were not supported by the data, an interesting interaction effect concerning the learning outcomes was found. Participants in the conditions in which only one of the interaction types was high scored higher on the knowledge test than participants in the conditions in which both types of the interaction were either high or low. An explanation may be that when the participants had to be mentally and physically active, this led to a cognitive overload and learning was hindered. This idea is partly supported by additional analyses of perceived task load, where descriptively, the two groups with the lower knowledge test scores scored highest on most forms of task load. In the study, we tried to separate mental and physical interaction, which may not be completely possible as mental interaction cannot be monitored from outside. For future work, the manipulations should be transferred onto other topics and situations, including more realistic and authentic learning settings. As could be seen in this study, it is possible to systematically manipulate AR learning material based on its characteristic interactivity. More experimental research is necessary to learn more about how AR can be used to effectively and efficiently support learning. And the 3 human-centered characteristics of AR, contextuality, interactivity, and spatiality, may provide a helpful basis for this. If you're interested in more information concerning this study or our research in general, please feel free to contact us.
Thank you for watching our video and goodbye.